during the first hour, we're saying a few words about electromagnetic waves. Okay, what we're going to deal with during the semester, whether how they were just a solution as a function of two variables, which was space and time. There was a solution of a differential equation. But now, before going too much into the further details, I just want to go over the syllabus. This is something that we have to do. But of course, the presentation of our waves, it took an hour. So during the semester, well, the course description is just aims for us to understand the time varying fields. Okay, we're not dealing anymore with static conditions. It's not that. So we have the time also. So once the time is also an important, or let's say, once time is a factor, changing factor, the equations become a little more challenging. So we have to observe for their solution. This is what this course is about. First, we're going to discuss about we're going to cover a small review of the Maxwell's equations, but either you want it or you don't want it, we will always deal with these Maxwell's equations in the first few weeks. Then, the second week, we can go over the time harmonic fields and the phasors. And by the way, all this information we're just going over, you can check this is the syllabus online. So if you just click at the course, you can see in detail the course. And then we are going to talk about the electromagnetic spectrum. So electromagnetic spectrum is just it's a range. Let's say it's a whole range of frequencies. So if we're going to deal with the waves, we often deal with the frequency of these waves. And once you have a broad range or bandwidth of frequencies, this is what we are going to call the spectrum. Of course, this electromagnetic spectrum. It is interesting because it is very wide. You are going to observe at least 5 to 6 orders of magnitude of difference from one band to another. Okay, so we may discuss about you can communicate with two different antennas using 1 kilohertz of information, which means that you can send a signal which has a frequency of 1 kilohertz, which means that in 1 second it completes 1,000 cycles. This is what it means, 1 kilo. But at the same time, we can communicate with higher frequencies. Any other frequency that you know that we can communicate with, other than a kilohertz, which I just reported it to you? What other frequency you have heard? Megahertz. What about other than megahertz? That's true. With megahertz? How many gigahertz? Like gigahertz, of course, the gigahertz is 10 to the power 9 hertz, so it's just a large number. So 3G, like 4G, this is the current communication. Most of the devices, antennas, they are compatible with 4G. So what I wanted to say is that if we can communicate with 1 kilohertz, of course, all of us know, even people that have Twitter science knowledge level of information, they know that up to 5G that we can communicate. So from 5G to 1K, it's around, how much is it? G is 9, 5 times 10 to the power 6 orders of magnitude. Then you can span, and you can have a communication. Of course, the communication frequencies are a little more wider. So we're going to talk about all the possible electromagnetic spectrum, and once in a while, often, we're going also to discuss about different type of communications when we're going to cover when we're going to do the examples. Then we're going to talk about the flow of electromagnetic power, Poynting vector, and Poynting vector. We might have covered this one also in the electromagnetic field theory that we had together the previous semester. We're going to talk about, then immediately after we discuss about the Poynting vector, which has to do with the power density, which is transferred by a wave. Okay, so once you have an electromagnetic wave, it does have some momentum. Okay, so you have an antenna, you turn on the antenna, and it starts to emit a wave. This one, someone can measure a pressure, which is because of this traveling electromagnetic wave. Okay, so this is something which is experimentally measurable. Then we're going to talk about the normal and oblique incidence. The normal and oblique incidence we'll just talk about the propagation of waves through different materials. Okay, so if it is free space, it's going to be something different. But if it is traveling through different mediums, where this could be a different medium. So a piece of glass, we have a cell phone inside, but of course, if the window is right here, this is a normal incidence. The incoming vector will be at an angle of 90 degrees. But if the window is like this, it's not normal incidence, it's oblique incidence. It's incoming with an angle. So, and they make some mirrors which will look skinnier, which is good. So if you are under stress, you just show up with one of these mirrors, and they do miracles. So after this normal and oblique incidence, we're going to talk about the waveguides. So once we start talking about the waveguides, this is really a very interesting piece of information. I'm calling it piece of information, or very important area of study, because this has several applications in several different areas. For example, waveguides is just it's a construct, it's a physical construct, which is also has dimensions, which has to be very nicely engineered for the sake of the possible applications. Sometimes they have to be very thin. Okay, sometimes they have to have precision with a very high level of precision. Sometimes the precision is not very essential. But for example, the last topic is that we might say some applications of cavity resonators. So a cavity is just a region where we have two mirrors where we can have full internal reflection. And you might need to have a perfect, so let's say, let me call it this way. I can call it, I can put 10 different terms, but let's call it this way. They have to be so much precise with respect to the distance between these two, so that they can decide whether the wave can be totally reflected backwards or not. So which means that a photon that goes inside, it will always be inside because of some physical constraints that we have put onto a wave equation, which now we have erased. So the whole course, it will be, we will discuss about the waves, their incidence. We're going to talk about the incidence of waves from a dielectric, and a dielectric is something which is not a very good conductor, but we can give more details about this one. We'll talk about how the waves propagate when they are incidents onto a conductor. So once a wave is incident on a conductor, many properties change. Some of you might know, for example, that what is a conductor? It could be, it's just a car. So if you are inside the car, if it is a purely, completely metal, which is a conductor, then the cell phone would operate much differently. But actually, the cars are not completely isolated, and they are not even intentionally isolated. For example, if you notice, old cars, they used to have an antenna at the back, but we don't see that one very often in the cars. Do we have any explanation for this? So old cars, they always had at the back this antenna. If you are playing football in the neighborhood, if you kick that antenna, it breaks very fast. You just run and you go away because the owner might get crazy. But nowadays, they don't have this problem. The reason is that these antennas, they are now in the windshield. So the windshield, the front glass of the driver, you might, if you carefully watch, you watch a conductive layer, black layer, which is like if you get an aluminum foil in the kitchen, it's a conductive layer. You can make an antenna with it. You just cut it very nicely, very thin. You put it on the windshield. It might be very nice so that even you might not even notice. And you have an antenna. So that's the antenna, which is going to pick up all the frequencies for the radio maybe, or some more information. At the same time, cell phones, they have their own antennas at the back. So if you have a problem with your cell phone, you open the back cover, it rings. You try to talk, you cannot talk because the back side of the cover, it has the conductive layer, which is serving as an antenna. So it enhances the signal. It has happened to me, and of course, it ended up you cannot talk if you remove the back cover of the antenna, because that is the receiving antenna at the same time. And what is also an interesting aspect is that in the first hour we talked about the parameters of wave. One of them was a wavelength. And what is very, to me, when I was a student, it was very much counterintuitive. Okay, so what was counterintuitive to me, it was that the wavelength that we communicate with, it has to be a direct relationship with the size of the antenna, which means that how big are the antennas that you use for TV channels? What is the size of the elements of the antenna? Puxa bir antenna person direction. But how big is the antenna? I mean, length scale. Let me call it this way. What is the length scale? Is it micrometer long metal pieces, conductors, or what? Or centimeters? Centimeters. How big is it? How?
It ranges from 30 centimeters to 2.
That's true. Okay, so from 30 centimeters to 2 meters, that is the length scale of an antenna. Now, what was counterintuitive to me when I was a student was this: is if the antenna, if the piece of wire is from 20 centimeters to 2 meters or 1 meter, the wavelength that this antenna can pick up, it should be of this order of magnitude. Okay, which means that these TV channels, apparently, depending on the size of the antenna elements that you measure in these constructs, this is the wavelength that you use. Okay, so now let's have a look now. If the length scale of our antenna, it's let's call it length L. If this is 20 centimeters, which is 0.2 meters, which is 2 times 10 to the power minus 1 meter. So if this is the length scale, then what could be the wavelength of this wave that is being picked up by this metallic conductor piece, right? So how can we do this? We can, so this means that the wavelength of the photon, a photon, we denote it like this, so, which is the carrier, the quanta of light. I mean, you might have heard this one before. So this is the wavelength, let's call it also the same. So this is also 2 times 10 to the power minus 1 meter. But then, let's see, so this is how large it is. What is 20 centimeters? Is this. This is 20 centimeters. You can measure a hand. This is, it ranges from 15 to 22. So that means that but now the question is that what is the frequency? How can we find the frequency? This is the question. First of all, before we find the frequency, we can ask the following question. What is the unit of frequency? Hertz, right? So let's try this one. So this, the unit of this one, it is 1/2 or hertz. Now, how, if we have three variables, three physical quantities, lambda, frequency, and speed of light. How, let me tell you that somebody tells also to me that these three are related. How could these be related together? Ce relațiune între că eu știți valid, frecvența știți adresis.
Lambda is speed of light over frequency.
Lambda is equal to
Speed of light
Over frequency.
Okay, are you sure about this?
Yes.
How can you make sure about this?
I remember.
That's good, you can remember, but at the same time, what we can try is the following. No, that's great. So this is measured in meters. Frequency is 1/2. The speed of light, this is meter per second. So these are the units that we have. If these are the units, then let's check. If we multiply these two, is it equal to this unit? Yes, it is. So it ends up, apparently, you are right. Okay, so the wavelength is equal to speed of light divided by frequency. So apparently, this equation that we just memorized, but if it happens that your memory is not, if you have some doubts about it, you can always check the units, and this should do miracles because you need to memorize this. So now here we just say the speed of light, it is 3 times 10 to the power 8 divided by. Okay, so we need to know actually. Yeah, we say the frequency, but we know the wavelength. Let's find this other one. This is 3 times 10 to the power 8 divided by wavelength, which is 2 times 10 to the power minus 1. So then we look at these numbers. 3 divided by 2 is 1.5 times 10 to the power 9. 10 to the power 9, yes. So this frequency, apparently, so this antenna that has an element, conductive elements of 28 centimeters, this means that the frequency is equal to 1.5 gigahertz. Okay. So this is somewhat, so if we can only communicate with this element of 1.5 gigahertz, make sure that this is also good at picking up signals which are 3 gigahertz. It's not a huge difference. The same order of magnitude is enough. Okay. So, I mean, can we push for 4 gigahertz into this antenna? Yes, you can pick the signal, but then there are some other constraints which we can discuss later. But something which is, which as I said, might seem like counterintuitive, but yes, the physical dimensions of an antenna, receiving or transmitting antenna, should be the same order of magnitude, like with the frequency that we communicate. If you look at the towers of cell phones antennas, often you might see a construct that looks like this. You have a bar like this, another one like this, and another one like this. If you look from the top, they are like they form like a triangle. So this is how they are most of the time. You might see these, and the dimensions of these it has to do with the frequency that they communicate. Okay, so so these are elements that we try to we see them quite some time during this course, and then when next semester when you do the antenna and propagation course, you might observe and you might be much better convinced about this important aspect. So these are the waves, and these are some important parameters. Another interesting aspect in the wave analysis. So if we have a wave, we can say that the wave equation can often be written like this: E is equal to E0. We need to associate some direction. So apparently, this is a wave which is polarized along the y-axis, and then here we have e to the power j gamma z. Okay, let's just analyze the spatial distribution. So here we have this important element gamma, and this gamma it is, we call this one propagation constant. Okay? The unit is clear. The unit of gamma is inverse meters, just because we have this meter next to it. Okay? So they are reciprocal of each other. They are inverse of each other. They are conjugate of each other. So there is a couple more synonyms that stands for this one: reciprocal, conjugate, inverse of each other, and also the units are also inverses of each other. Now this gamma, and here we see j, which is square root of -1, and this gamma, this can be written as alpha plus j beta. So often we end up into having a propagation constant which has a real part and a complex part. Now, if you talk about a system, but the details of this one, of course, we're going to do this one very, very carefully in the next weeks. Now, I just want to talk about a little bit about the applications of these. We're not going to derive this one. So this piece of information we're going to cover again. Don't worry too much. You're not going to lose if you're not very attentive. But what you should not forget is this important element, which can be applied in different areas. Now, here we see this propagation constant, which is carrying two different components. One is the real, one is complex. And so one of these, it shows up itself. One of these is always there, okay? Which means that if it is any type of material, like a piece of wood, so this one is a piece of wood. Or sorry, this is not the. This seems to be non-transparent to optical frequencies. So, for example, you cannot see a laser. If I turn it on from this side, you cannot see on the other side because the wood is non-transparent to optical frequencies. But it's not non-transparent to cell phone signals, right? If you are in a cottage made of wood walls, of course you can use a cell phone, right? But now the problem is that sometimes if you are in an elevator, if you are in some other country, if you are stuck in the elevator, you cannot call the police because the signal is very weak. The signal is very weak for health reasons. Here in Albania, signal is higher for health reasons, but not for good. So if you are stuck in an elevator here, you can call they will answer to you. But the point is that the signal is slightly weaker because it's a very good cavity, because it's a conductor. The elevators, they are made of, sometimes they make them out of glass, so you can always call from an elevator. But if it is fully conductor, what happens is that this propagation constant, it has an extra term, because conductors are, once a wave is passing, conductivity, it causes some absorption of the signal, okay? Now, overall, what happens is that these two parameters are very important, because sometimes you can apply this in important areas, such as this one. Microscopy. Microscopy, what is microscopy? Traditionally, we use a light source, which can be used at the bottom. This is some light source. This can be LED. Yeah. LED is a good light, it's white light. It can also be provided with a very good uniformity. And then on top of this white light, you can put some microstructures. What is a microstructure that we see it a lot, but we never are aware that it's very microstructure? There are many. You can pick up the nest of a spider. Those nice thin things are microstructure, are very thin. A piece of hair is 40 micrometers. So this is how thick it's a hair. So you can, but also human cells, a cell, cheliza, this is the size of 8 to 10 micrometers. So it's a microscope. This has to do something with micrometer. We talk about 10 to the power minus 6. All these numbers, we put them together. It's always microbus, minibus. And then, so here you have the light, and here you can have a camera. So once you have a camera here, what is important for a biologist or for a scientist is to being able to record this structure here, to record it here. Now, in order to record it, there are two different approaches that can be used in microscopy. One of them is the following. This information, it hits the cell, and then it drops onto the camera. But since the light is going to be absorbed, we get a darker spot on the camera. Okay, so if it is the background, you have too much light in this region. But if the light is passing through some object, if the object is dense, you get a darker spot in here. So if a cell has, what is a cell? It has two major components. One of them could be this one, the nucleus. The other one, it's called cytoplasm. Nucleus, it has a higher density, and what one can observe into a camera, and this information on camera with the USB connector, it is shown into a screen or a monitor. What you observe, you see some dark regions here. Then you see some other region which is not that dark, but it's a little brighter. And here it is very bright. Okay? So how did we observe this biological system? By just noticing that if I lose some part of the intensity because it's absorbed, then I have a darker region. So this is how we observe this one. What did we make use of? We made use of this attenuation constant. Okay, so this is called the attenuation constant because it's as simple as putting an obstacle in front of some light source. You have a light source, you put your hand here, you see the shade at the back side. As simple as this. Now, this was the attenuation constant, this alpha. Then another important constant, which is relevant during the interaction of waves with a biological system or any other system, is this phase constant beta. This phase constant. Now, what the phase constant does is that sometimes the attenuation might be very low. So which means that if you want to do microscopy, if you want to see the a biological sample, you might not observe it, but what could be observed is the following. Let me think for a moment. Yeah. So let's assume that here there is some piece of glass, and here there is another piece of glass. This has beta 1, this has beta 2. Light source is everywhere and it's going like this. And now we have two different mediums that have different phase constants. So the index of refraction might be different here. So we know index of refraction, let's say that this is N1 and this is N2. So you can call it a medium which has a gradient of the parameters. When you say a gradient, so you go a little further, there is a different environment, so to say. Now, nowadays, we are very good at signal processing, which means that this beta 1, what it has to do with a wave traveling like this over some distance. So this could be beta 1, but then this other wave, it might travel a different path, and here we can call this one, these two waves, they started being in phase, each in the phase finished, but afterwards they are out of phase. So now what the researchers can do nowadays is that they can just compare the phase difference of light sources coming on different pixels, okay? Because this information, it is projected down onto a camera, which is composed of pixels, and these pixels nowadays, they are very good. They can be made as small as 1.4 micrometers. This is not the smallest. This 1.4 micrometers, you can buy it for 150 euros. It's very cheap. So, I mean, you pay some more, you can get half a micrometer. So now, on different pixels, we are acquiring these two signals, and we notice that these two pixels, they have light source, which is at the same phase, okay? But this light source, it has a different phase. So what do we mean with different phase? Maybe we can show a comparative example. So we can use in microscopy or for detailed information acquisition, attenuation constant, we just meant making some pixel darker than the other, or it can be something like this. So two waves, they start at the same phase, like this. So these two are in phase because the maxima are at the same time. The minima are at the same time. The maxima, again, they are at the same time. But we might end up with some delay on a specific pixel if the light source has passed through a different material with different properties. We might end up getting a peak, which is something like this. Okay, so this is going to require its peak a little later. So this is the delta time. Okay, if this is the time which is measured in seconds. Okay, now this is the delta t, and but yeah, this is the delta t. We can convert now these units in all the different possible units. Okay, so if this is delta t, we can also find what is the delta frequency, or how can I write this? Because this is the delta t. So let's try to make some equivalent principles. Well, let's use this way. Let's assume we're trying to do microscopy with optical. Well, this is not optical actually. Let me think for a moment. No, 1 gigahertz information is not optical. But some of you might help me. What is some wavelength which is in the optical range? What colors can we see? What? Is it nano? I always forget. I just remember. But how much nano? How many?
700 nanometers.
So nanometers is not nano. I mean, why? No, you are correct. Exactly. We see something from 400 to 700. This is what we see. And for sure, this is nanometers. Okay, 200 nanometers, it should be micrometer, which is good. But anyway, so this is the microscope I operate with. So what does this correspond to? This corresponds to 0.7 micrometer. So we can write this one whichever way you choose to do. So this can be 7 times 10 to the power minus 7 meters. Okay. So this is 7 times 10 minus 7. Okay, that's good. And then what is the next relevant wave component? So okay, we get here one number. That's cool. And another thing is following. So we call this a microscope, so we can observe anything in the range of micrometers, and the wavelength is also micrometers. Okay, so the wavelength, we talked about this one, so always the communication, the detection, the spatial resolution, they all depend on this one. The size of the antenna is related to the wavelength and all of these issues. So apparently, this lambda is this much. But now, how can I bring together this discussion here with a shifting in the frequency like this? So first of all, let's try to determine what could be one period, such period. So a period is something like 2 pi over lambda. This is something like, or no, sorry, this is not, this is k. This is k. The period is 1 over frequency. So what is the frequency? Using these expressions, the frequency, it was c divided by lambda. So this is 1 divided by c. Lambda over c, that's true. So lambda is 7 times 10 to the power minus 7, this is meters, divided by 3 times 10 to the power 8 meters. So there is something missing here. There is a unit of, this is seconds. So 7 divided by 3, this is 2, approximately 2. And this is times 10 to the power minus 15 seconds. So we are measuring not picoseconds, but femtoseconds. So this is 2 femtoseconds. So this is, so this from the maximum to another maximum, we are talking about 10 to the power minus 15 seconds. Okay, so this is what we are talking about. So if apparently, if we have phase change, apparently it would be something like, let's say, 1 order of magnitude smaller, or a quarter. Mine cherry on the side. That's why cherry. So it looks like this. What could be the delta T phase change, which could be measured because of the phase difference between two different regions of the same biological sample, which could be changing as a function of space. We might be talking something about like 1/4 of 10 to the power minus 15. Okay, that's one parameter that we can extract. Another interesting parameter that we can try to extract from here is, let's try to see how much is the phase difference. Now, a change from peak to peak in the phase space, that's in phasore, it is 2 pi radian. So this is 2 pi, okay? And then, how much radians are we shifting if it is a quarter of a femtosecond? Cuboid. So if you have 2 pi phase difference, how much time difference was it corresponding to? It was 2 femtoseconds. 2 times 10 to the power minus 15. Now, what did we get? We said that what if the phase difference is a quarter of a femtosecond minus 15? Then the phase difference is pi over. Let's try. You are right. Or pi over 4. Let me see. I'm not very good at this calculation. You can help. This is 2 times 1 over 4 divided by 2. It could be a quarter. Pi over 4. So x, it could be a phase difference, which is pi over 4. But is it correct? Okay. So it looks like, but what is pi over 4 phase difference between two waves? Well, if it is, what is pi over 4? We can compare a cosine with a sine. Now, actually, we draw it out there, but once you put some numbers, maybe the phase apparently it ends up to be pi over 4. So, what is cosine theta? Cosine theta, it's 1 at the 0. So, let's draw a cosine. It's 1 at the 0. It's 0 after some period here and here. This is a cosine. And what is this? Phase difference? 2 pi, that is correct. That means that this phase difference up to here is equal to pi. This phase difference up to here, this is just pi over 2. Apparently, we're going to get a phase difference of pi over 4, which is going to be half of this one. So that means that another wave, which has a phase difference of pi over, that means that this peak will be right here, okay? It's going to be shifting by this much. And also this minima is going to be somewhere here. So we do it like this. I mean, this is the best that we can do on the board. So we have electromagnetic waves. We said that we can not only the attenuation constant, which means that I have light, but I put my hand here and I observe shape like this one here. We don't always just notice the shade compared to the background, which is brighter, and the shade, which is darker. But also, we are good enough nowadays to measure different phase differences from the same, from two neighboring pixels on a camera. Now, these are some essential elements that if someone is working in this interesting field of imaging or microscopy, these are the essential or the basic fundamentals that drive our understanding of the image acquisition, image processing, or signal acquisition. Do you have any question